Ilhan, did you start it? Ilhan, did you start recording?
No, Muhammad Uskan is recording right now.
Mohammed, did you start recording? Then you need to stop it, okay? Because if I stop it, it will be messed up, okay? Don't forget to stop recording at the end of the lecture today.
So now you can start to record. And no one's recording right now.
But did you stop it? Okay, I am starting the recording now, but there will be two videos. I think it is recording right now. Okay, it is recording. Okay. Okay, good. So I am recording the OBS. Okay. Next time, don't start recording. Okay, just let me know, and I will start it. So the interrupts are important. We said that. Okay. And with the help of the interrupts, it is possible to conveniently have more than one process seemingly running on the computer at the same time. So this number 6 says that after you handle the interrupt, you don't go back to the interrupted process. Okay, the scheduler chooses which process to run next. Okay, we choose a process scheduler. Okay, no, sorry, number 6. We choose a process to run next. So that doesn't mean that we go back to the interrupted process. Interrupted process could be suspended, or it could be blocked for a few, could be where would I put the interrupted process? In the blocked state or the ready state?
Ready.
It is in the ready. It is in the ready queue, right? Why? Because it was already running. It was happy with the CPU, right? Everything is fine. Then interrupt happened. I have to interrupt it. So that process could continue if I wanted, but there might be other processes to run next. It is up to the operating system to make that decision. Okay, so let's look at this multi-programming again. Let's say I have a process number 1, P1, process number 1. Okay, I have a single process, P, and it is, let's say, 30%. That process P is waiting for input output for 30% of its time. Okay, so 70% of the time it is using the CPU, 30% of the time it is waiting for the IO to happen. And if I don't have any other processes to run, that means that my CPU efficiency is what? What is my CPU efficiency? If I am only 70%, right? It is just 70% efficient. Why? Because I am waiting 30% of the time. I am waiting for 30% of the time for some IO. You might say that the operating system might be doing something. Okay? I mean, in that 30% of the time, maybe operating system is taking a backup. It is shuffling around the process table, etc. But that's not a useful time for me as a user. Okay, as a user, I am only concerned with my user processes. Okay, how much batch process I did, and etc. So that's good. Let's say I have another process. Okay, I have another process. Let's say this is P1. Let's say I have P2, and P2 is again 30% wait time. So I have two processes. That means that if P1 is waiting, okay, if P1 is waiting, then I can let P2 use the CPU, right? So I could be more efficient. But P2 might be waiting for the input output too, okay? So what would be my CPU efficiency, okay? So the worst thing would be, I mean, it could be either P1 is using the CPU, P2 is using the CPU. Well, how many states do I have? Okay, how many states do I have? Let's say P1 and P2. It could be, it could be 1, 2, 3, 4. This is busy, and both of them busy. It could be both of them busy, right? Okay, let's do this. P1 is running. P2 could be either blocked or, let's say, running is RU, right? P2 could be either blocked or ready. Is that true? Yeah. When P1 is blocked, okay, or ready, P2 could be blocked, or maybe, okay, let's do this. If one of them blocked, the other one could be blocked too, right? That's true. If P1 is ready, P2 could be ready or blocked. Let's say ready or blocked. This could be running. Can you think of any other case? Both of them cannot be running at the same time, right?
One can be blocked, the other can be ready.
That cannot happen.
But let's assume
One of them,
okay.
one of them is blocked. The other one cannot be ready because the other one would use the CPU in that case.
But we said there is like 30% wait, so there is a big chance.
Ready means that it is ready to use the CPU. If one is blocked, the other one cannot be ready because if one is blocked, the other one is running.
Okay.
Or if one is blocked, the other one could be blocked. If one is blocked already, the other one. I mean, you cannot say that one is ready, the other one is ready. Both of them cannot be ready. Okay. If one of them is ready, the other one has to be using the CPU because if one is ready, then the operating system will let it use. Okay. So I am after this. Okay. I will say that. What is the chances of that both of them are blocked at the same time? That's a bad situation. I don't want that, okay? So what are the chances that both of them are blocked at the same time?
If they are waiting for different resources,
Yes.
then they can wait at the same time.
So what are the chances? Give me a number.
If we assume that all of these have equal chances, then it is 70 times 1 over 5.
70 times 1 over 5? Where is 5?
Yes.
Where did you get the 5?
Running block, running ready, blocked blocked, ready running, blocked running.
Well, you cannot assume that each one has a same chance. I gave you the number here. P1 is the possibility of if I ignore this P2 line, if I ignore line P2, okay, so there is a 30% chance here that it is blocked. The rest of them is 70%.
Oh, okay. So
But I know that there are two processes and there are two processes, and each one has a chance of 30% I/O wait time. So this one has a chance of 30%, this one has a chance of 30%. So if I do that, this would be, okay, 0.3 times 0.3. That means that,
9%.
okay, 0.09, okay, there is a 0.09 chance of both of them are blocked. So what is the efficiency of this CPU then?
Don't they independent percentages? They are dependent on the
They are
program.
independent. That's why I can multiply them. They don't depend each other. They are not waiting for each other. Yes, that's true. They are independent. That's why what is the chance of P1 is waiting for I/O, and what is the chance that P2 is waiting for I/O? 30% this one and 30% this one. If I multiply them, so there is a chance that 9% of the time both of them are waiting for I/O, right? So what is the efficiency of this system now?
91%.
91%, exactly. 109. It is 91% of the time CPU is going to be busy. So previously it used to be 70% with a single process. Now I am 91%. That means that running more than one process is good for the CPU utilization. That's good. So if I run three processes, what happens? Let's say I have P3. So in that case, it's going to be 1 minus 0.3 over 3, right? So that's going to be about, it is 21, right? 0.021 is going to be about 98% CPU utilization. Okay, so that's the idea. That's the idea. That's how you do it. The formula is this: CPU utilization is, okay, 1 minus p to the power n, and p is the I/O wait time, block waiting time, not ready time, but block waiting time. Okay, when one process is ready, that means that somebody is using the CPU, so the CPU is not sitting idle. But if a process is blocked, and all the other processes are blocked, then nobody is using the CPU. So this is kind of a, okay, this is not a very realistic CPU utilization formula. It's just a calculation. Okay, it's just a calculation. But this one assumes that I can add any process to my computer, as many processes as I like. N could be very, very large. For example, N could be 100 or 200 or 1000, right? But this cannot happen. Why? Because I have limited amount of memory. If I run too many processes at the same time, try to run too many processes at the same time, then I will run out of memory, and in that case, no, that will not be good. Okay, let's look at this example then. Now, okay,
So what we calculated was just for one CPU and for one core only, right?
Yeah, of course. What did we say at the beginning of the chapter? If I don't say otherwise, in the chapter we always assume that we have a single CPU and we have a single core.
Oh, all right.
If you have more than one CPU, okay, if you have more than one CPU, then that means that you need to multiply things by 2, because since you have one. Okay, if you have a single CPU only, and if you have a single process, that means that, okay, 70% of the time I will be using one of the CPUs, the other one will be always wasted. Okay, if you have two CPUs and if you have two processes, that means that again 30% of the time one of the CPUs will be idle and 30% of the time the other one will be idle. Okay, the calculations are similar, but for a single CPU, this is our calculation. Using this formula, okay, CPU utilization formula, okay, the book gives this figure to 2.6, says that depending on your p-value, these are my graphs. Degree of multiprogramming or the number of processes versus the CPU utilization. If my P is 80%, okay, what kind of process is this? Give me an example for such a process. It is 80% CPU utilization. Sorry, if it is 80% IO weight.
Keyboard?
Calculator.
Yeah,
SD
okay.
card maybe.
By keyboard, I think Mohammed means that it's a process that uses lots of keyboard. It's waiting for the user to type something, or someone says that calculator is waiting for the user input to, that's true. So it is doing lots of wait. It is waiting for the user to enter something, right? So that's kind of so for those kind of processes, they don't use the CPU much. They always wait for something. Okay, so if I have such a process, okay, if I have a single process in my memory, then my CPU utilization is 20%. If I have two processes, it is 40%. If I have 10 processes, it is still barely about 80%, right? Barely about 80%. Okay, but if my IO wait time is 20%, that means that maybe this is a compiler or something. It is doing lots of stuff, but still compiler has to read lots of data from the disk. But once it reads all the data, then it will keep compiling. Okay, so if I have a single process, I am utilizing my CPU 80% of the time. If I have two, it is well above 90%. After three, my CPU is very efficiently used. Efficient use of CPU is something good, but sometimes we don't like it much. If my CPU is 90% busy, if my CPU is 90% busy, for some cases I like this, but for many other cases I don't like it. Tell me for which cases I don't like 90% busy CPU times.
Mobile device.
And a mobile device, why did you say that, Yusuf?
Power consumption is too high.
Yeah, power consumption is too high. Tell me another reason. I don't like
User
this.
interface may be laggy.
Yeah, if my CPU is 90% busy, then my interactive processes will have less time to use the CPU. That means that their interactivity will not be as good as I want. So for interactive processes, you like to keep 50% of your CPU time free because you don't want to keep alert, okay? You don't want to keep interactive. Whenever there is a key press or screen touch, you want your computer to respond immediately. Okay, so for the mainframe computers, you want your CPU to be very busy. Okay, but for your mobile devices, for your everyday computers, you don't want your CPU to be busy all the time because that will lessen the responsiveness of your computer. Okay, so these are all good graphs, and the book has another good example about this modeling of multiprogramming with the formulas. It says that, okay, let's say I have a computer of 8 gigabytes now. Okay, now here we didn't consider the memory amount, the amount of memory that you have. Now I have the memory now. Okay, a computer has 8 gigabytes of memory, so it is limited. Operating system takes 2 gigabytes of memory. That means that 6 gigabytes only available for the processes. Okay, I have, and this one says that operating system takes 2 gigabytes and each user program, each process takes 2 gigabytes of memory. So that means that I can run at most 3 programs at the same time. So that means that if my process is 80% on average is waiting for the I/O, that means that I could use at most this much. I have to draw a line here. Okay, anything beyond this line is not possible anymore. Why? Because I don't have enough memory. That means what? That means I will be only about 50% efficient, because my memory doesn't let me load more than 3 processes at the same time. Okay, so that's the constraints. Okay, so I like to, so that's what it says. 1 minus 0.8 over 2 is about 50%. So let's say if the memory is not that enough, then let's add 8 gigabytes of more memory. If I add 8 gigabytes of extra memory, that means that now I can run 6 processes like that. So it's going to be around 80%. So by adding this much memory, 8 gigabytes of memory, I gained 30% more efficiency. Okay, so this means what? By using more memory, I will be able to utilize my memory even better. Okay, so memory has a very strong influence on the CPU utilization. More memory means better CPU utilization. Or let's think about this. I have an interactive device. Okay, I have an interactive device, and I see that my responsiveness is not that good. Okay, I am using 80% of the CPU time. How would I increase the interactivity of my computer system? You add more memory. When you add more memory, then since you have more memory, okay, you will be free to add more processes to your system, or you may choose to keep it that way, and your utilization will be better, and your responsiveness will increase. Okay, good. So by adding 8 gigabytes of more memory, my utilization will increase from 50% to 80%. Okay, so that's nice. So that's a good thing. That's a very good thing. Okay, 8 gigabytes of more memory, 30% more CPU utilization. If I add 8 gigabytes more, let's do that. If I add 8 gigabytes more, that means that I have a total of how many processes can I run now? I have now 24 gigabytes. Is that correct?
True.
24 gigabytes means that I can run 22 and 11. Yeah, I can run 11 processes. And 11 processes means that it's going to be around 85%, right? 85%.
I think you meant to write 7 instead of 6 because 6 processes means uh, like what? 12 gigabytes and 2 gigabyte OS, 14 gigabytes.
You are exactly right. So by adding 8 gigabytes, I can run now not 6 but 7 processes, right? That's true. So this is okay. So now I can run 11, right? By running 11 is going to be around 85%. So this time I increase from 80% to 85%. Well, just 5% increase, not much. Would you do it? I mean, okay. Would you do it? Depends on the memory price, depends on your needs and etc. Okay, 30% was a much better deal than 5%. Okay, the same 8 gigabytes in this case gained me only 5%. So this is 30% gain. But if I do here, then I will get only 5% because it's going to be around 85% CPU utilization. Okay, good. Any questions so far? So this is simple mathematical analysis of the CPU utilization, but we ignored many things. For example, we didn't say that there is an operating system and it is using the CPU and there is the switch time, etc. And we assume that all the processes are the same. Not all of them are the same. Okay, you may not assume that each process is going to be 80% IO weight, IO bound. Okay, but still it is better than nothing. We can use this kind of analysis to make a decision on how much memory we need for our computer. Okay, now you understand by mathematics the effects of memory on your computer. Okay, so by adding more memory, your computer will be more responsive. Okay, because you will have better CPU utilization. Okay, but after some time it doesn't matter much when you add more memory to your system. Okay, if there are no questions, then I will continue with a new topic. Okay, so remember what we have kept in our process table. Let's go to the process table. Where is process table? What do I keep in my process table? Yeah, these are the things that I keep in my process table. Okay, I have to keep this data in my process table because if I switch from one process to another process, I have to save them, and for the new process I need to load them from the table to the registers and etc. Okay, this is called resource grouping. Resource grouping. Many resources, okay, like the CPU is a resource, and I need to keep information about the CPU resource. Okay, for the file management, open files and etc. and my current directory, that kind of stuff. I need to know all of them so that I can keep information about the processes. Somebody said maybe 30 years ago that somebody said that, okay, this resource grouping is good. Okay, this resource grouping is good. What if within a single process I can run more than one function at the same time, seemingly run more than one function at the same time. let's say I have function f1 and function f2. It is in the same program, and I like to run them at the same time. Okay, first run f1, then after a while run f2. F2 if f2 is blocked, then run f2 f1, etc. Okay, so I am not switching between the processes, but I am switching between the function runs. Well, in that case, f1 and f2 will share many things in this process table. For example, my root directory, my working directory, my file descriptors, they will all be the same. So when I switch from f1 to f2, okay, when I am running them, I don't have to switch all of these. That means that I can run two programs at the same time, but these two programs are related. They are sharing lots of stuff. So the context switching will be very, very cheap. Okay, because I am not changing my address space at all, and they will be using the same memory address. Okay, they using the same memory space, the same address space, in fact. Okay, so if they are using the same address space, switching between these two functions, running these two functions will be very, very cheap. So that's the idea of threads. Okay, that's the idea of threads. Okay, like processes, threads are programs in parallel. Okay, we usually use threads like this. We usually show threads like that. Okay, this is our computer system. This is our hardware. On top of hardware, I have my operating system, and in the user space, I have my process number 1. In my process number 1, okay, I have lots of data like the open files, network connections, signals, alarms, and etc. Okay, I have my stack space. Okay, I have my register and etc. And there is a thread running. This is a running thread. This is an execution. It is just execute this instruction, then next instruction, and next instruction. Okay, the idea of a thread is this: why do I run a single thread in a single process? Let's run another thread. So running another thread means that that thread has to have its own registers and its own stack. Okay, this is stack number 1 and this is stack number 2. This is thread number 1 and this is thread number 2. Also, this one has its own register set, and this one has its registers, R and R. By register, I mean all the registers, including the program counter, stack pointer, program status word, and etc. Okay, but all the other stuff that you see in the process table will be shared between these two threads. And most importantly, the address space is the same. Okay, and there is no protection between these two. I mean that T1 is free to access anywhere within the address space of P1. T2 is the same, it can do the same thing too. Okay, T1 and T2 can write to the same address space, can read from the same address space. So there is no protection between them. Okay, but if I do another process P2, of course I know that the thread, the execution of P2 won't be able to access the address space of P1. It is protected by the operating system and the hardware. Okay, so these are some of the differences between the processes and the threads. Okay, like processes, threads are programs in parallel, but unlike the processes, the threads, they share the same address space and data. Okay, so they are free to use each other's data. And the advantages, they are lighter. Okay, they don't need too many resources, many resources, and they are faster to use. Okay, especially for the initialization. Okay, for some systems, instead of running two processes, if you run two threads to do the parallelism, you will gain 10 to 100 times more CPU time. Okay, so they are 100 times faster to start initialize. Okay, of course, I mean, if one thread is CPU bound, if one thread is trying to use 100% of the CPU, then there is not going to be much gain. But if a thread is like maybe 80% time is waiting for the I/O, then of course using more than one thread is going to be very, very efficient. And another thing is there is no protection between the threads. That's what I said before. Is this a problem for the operating system and the whole computer? A security problem? No, because the threads are written, okay? Whoever writes this T1 writes T2, so they are part of the same process. So the same developer is writing both of them, and the same developer knows that T1 and T2 share the same address space. Okay, there is no intentionally, there is no protection between them. Okay, intentionally there is no protection between them, so that they can freely share the same address space and they can communicate with each other very, very efficiently. Okay, there is no protection between them. It is not like P1 is written by one person, P2 is written by another person. They are two different people. Users are using the same computer. No, it is not. Okay, it is not. So think P1 as, for example, P1 is Internet Explorer. Internet Explorer. Okay, T1 is a tab, T2 is another tab. Okay, so both of them are part of the Internet Explorer, and each one is running a different tab. For example, when I open my Chrome, okay, when I open my Chrome browser, okay, I could load one web page here and another web page here, and as you see, both of them are loading at the same time. This one is having lots of difficulty accessing the web. This one is having the same difficulties, but they are running their own difficulties. I bet this one is being blocked all the time because it's waiting for the network, and this one is waiting for the network too. But they are doing two different things, but they are part of the same program. Okay, they are part of the same program. So, and this kind of structure is written by the same person, by Google or Microsoft, whatever. So we say that, that's why, just a minute, we say that the threads, they cooperate. They are designed to cooperate. They are not designed to compete. Usually the processes compete for the CPU. The processes think that I have the whole computer, I have the whole address space for me, and I have the whole CPU for me, and I will use the CPU and the memory the way I want. The threads, they don't assume this. The thread assume that there is another thread, and I have to be nice with the other thread because it is useful for me. Okay? If I make the other thread's life miserable, then my life will be miserable too, because we are helping each other. Okay? So threads, they cooperate. They are designed to cooperate. Processors, they are designed to processes. They are designed to run by themselves. Okay? The only thing they think, the only thing they care about is themselves. Okay, question.
Yes. So let's say we have a program with two threads and another one with a process with two threads and a process with only one thread. Will the process with two threads run twice fast as the process with one thread, or will it take more CPU time compared to the P2 or second process?
No, Usama, we are going to talk about it later. It depends on your operating system structure.
All right.
Okay. I mean, there could be many processes, many threads here, like 6 threads. If operating system knows about the threads, maybe this one is going to take more CPU time. But for some systems, operating system doesn't know anything about the threads, because threads are happening within the process. Okay, operating system thinks them as part of the same process. So for the operating system, there are 2 processes for this one. Okay, but for some cases it is different. For some cases, operating system knows about the threads, because you need to make system calls for to create threads. But we will talk about them. Yeah. Okay, so threads are lightweight processes. Okay, they are processes, like they run in parallel, but they share many things. Okay, so these 2 threads, they share many things, especially the address space. When you share the address space, you are sharing what? In terms of hardware, you are sharing, if you share the address space,
Memory?
you are sharing memory, definitely. And if you share memory, then your cache hits will be very similar. You are sharing the cache. Okay, and invalidation of the cache, when you switch from one process to another process, is the one that takes lots of time. Because if you switch from P1 to P2, okay, your cache will be invalidated, and filling in the cache and getting your program up to speed is going to take a while. Okay, but with the threads, that's not going to happen, because you are saving you are using the same address space. You are not going to, security is not a problem. You don't have to invalidate your cache or memory lookup tables and etc. So that will be very, very fast to switch between the threads. Of course, it's going to take some time. Why? Because each thread has its own register set. Each thread has its own program counter, program stack pointer, all the registers, A register, B register, etc., whatever your registers you have. So you need to store the registers and you need to load them again, but you don't have to do cache invalidation, virtual memory table build up, and etc. Okay, good. Any other
I have a
questions?
question.
Sure.
We know how to change program in the CPU, but who decides which threads work? I mean, this for P1 have 2 threads, and which one gonna work when P1 take the CPU time?
Yusuf, I am going to answer this maybe in next half an hour, and it is very similar to what Usama has asked a few minutes ago. I mean, depends on your operating system structure. Okay, yeah. So both of you are asking me who is managing the threads. Okay, we know that operating systems manage the processes. Why? Because in the operating system address space, there is a process table, right? Process table. Within the process table, you have all the information about the processes. So when the time comes to scheduling a new process, operating system looks at this process table. It sees which processes are ready to run, okay, and it chooses an appropriate one. Okay, that's what we know. So both of you guys are asking me, who is going to make this decision for the threads, operating system or the processes themselves? Okay, I'm going to answer that in a few minutes. Okay, so the idea of a threads is this: if you are writing a program, nowadays especially, okay, you like to do things in parallel. Okay, the example usage is, for example, that browser, Internet Explorer or the Chrome browser, you are showing many pages at the same time, and they have to run in parallel. Okay, one of them could be loading pages, the other one could be showing some video. The other one could be showing some graphical display and etc. But each of them should be running in parallel. But they are related. I mean, I don't want to make each of them, I don't want to make each tab as a new process, but I like to make it each a parallel thread. Okay, so one thread may block from time to time, and I am going to continue with the other. Another example is for example, your Word editor. Okay, Microsoft Word, for example, when you run Microsoft Word, it does many things. It does many things. For example, it keeps taking backups. Okay, it keeps taking backups. If your program crashes, okay, if something happens, you know that there is a backup of your Word document. I know that. So a thread continuously keeps taking backup of your data. That's one thread. Okay, so this is your process. This is your process P. Process MS Word. Okay, Microsoft Word, and it is running 3 threads inside it. A single process, but it is running 3 threads inside it. This thread is responsible for taking backups. Taking backups means that you don't take the backups every other second, right? You take backups maybe every 5 minutes. For 5 minutes, this thread is blocked. It is waiting until the time comes, that 5-minute interval, and it keeps taking the backup. It keeps writing the data to the disk. Writing to the disk is a I/O bound process. That means that it's going to wait lots of time for the disk to finish up its job. So that's the I/O. This one is for formatting the screen. Okay, so whenever I type something, okay, the screen has changed, and somebody has to draw the screen on the monitor, the document on the monitor, and this one is responsible for that. Okay, so if there is no change on the document, then the screen will be the same. It's not going to do anything. This process is responsible for taking the input from the user, either in the form of keyboard or from the mouse or from the touch screen. So as you see, there could be many more threads running in my Microsoft Word. Okay, and it is difficult to write a single program that handles all of them. Okay, it's going to be a very large loop. First check the keyboard, then if the time is up, take the backup, and if the screen needs to be updated, then update the screen, etc. So I have to be responsible for all of them at the same time. It's going to be very difficult to write if it's going to be very difficult to write these kind of programs, because I need to do lots of stuff at the same time. Instead, let's say I have a function f1 which is responsible for I/O, function f2 responsible for updating the screen, function f3 is responsible for interacting with the user by keyboard or the mouse or the touch screen. Okay, so each one will be very simple function. Well, compared to the complicated function, each one will be simpler. Okay, and each one will be running in parallel. If one of them is blocked, then the others can go on. Okay, so that's one example case for a thread-based program. Again, this is a single process, but it is running many things at the same time. It is seemingly that way. Another example is here a multi-threaded web server. Okay, this is my web server, but it looks like I am out of time. Let's take 10 minutes of break. After the break, we will continue with this example. Okay, and I'm going to show you some code about that example. Okay, so let's be here around 11:35. 10 minutes. Okay, so this is the second case for a sample multi-threaded application. This time we are going to use a web server. It's not an interactive process, but it's a server process. So the server process has, in this case, one main thread. This is called the dispatcher thread. The dispatcher thread is connected to the network. It waits for the clients to connect and ask for web pages. Okay, somebody's connected. Let's say this is our Gebze Technical University server. Okay, somebody's connected and they like to view the computer engineering web page. Okay, so this one takes this request and it hands over this request to one of the available threads. Okay, so these are worker threads. They are available and they are waiting. Let's say I have 10 threads waiting. They are in the block state. They are waiting something to hand over them to somebody to hand over them to load some pages. So dispatcher thread takes the request from the network and it dispatches one of these threads, and again it starts waiting for another request. Okay, as long as there are available worker threads, this will continue. If there are no worker threads available, then this one will send a message to the client saying that the server is too busy. I cannot answer you right now. Please try back later. Okay, sometimes you get this message, right? The server is too busy message. It doesn't happen often, but it happens from time to time. Again, this web server is a single process, but it keeps running many threads. One of them is the special thread, dispatcher thread. Okay, its job is take the request from the web and hand it over to one of the available threads. Okay, and these are very simple too. They take the job and they show it to the current client. Okay, let's look at the simple code, overly simplified code for the dispatcher thread and the worker threads. Okay, so this dispatcher thread is this. It's run in an infinite loop. Get the next request from the web, and it hands off the work to the worker threads. So this one selects the available thread and unblocks it, and it keeps running. This one is a code for a single worker thread. Okay, it waits for the work. Okay, if the work is available, then okay, it sits here most of the time. It is idle in this function. Okay, it is waiting. When the data is available, when the request is available, then it says that okay, I am going to see if the page is available in my buffer, in my memory. If it isn't available in the buffer, then I am going to return the page. Otherwise, I need to get that data from the disk. So getting the data from the disk requires many IO requests. So it will be probably blocked in this state. But if the data is ready already in the cache and the memory, then it is immediately return this page. Okay, so this time two special threads, dispatcher thread and the worker threads, but previously I had 3 different threads. Each one has a single copy. This one, the dispatcher has a single copy, but the worker threads has many copies. Okay, a second example that uses the threads. Again, each thread is responsible for doing something, but each one knows that other threads are running and they are doing similar stuff. They are helping each other. They are cooperating. Let me go back and let me underline this again. Threads cooperate. They are designed that way. They are designed to cooperate. They don't compete. Processes, they compete usually. Okay, the processes, they usually compete, but the threads, they help each other. Okay, I mean, This thread without other two threads doesn't mean much. This thread without the display thread doesn't mean much. Okay, so they need each other's help. Okay, I guess somebody has a question. I don't know who that is. Doruk, okay. What's your question, Doruk?
Yeah. Maybe you already mentioned, but I couldn't understand. So normally for one cycle processor, when multiple programs work, they are in race condition, and we don't know which one will work more. But for the threads, when we have multiple threads, how does it work? Like one stops and other continues, or how can they work in parallel?
Again, I think this question is related to what Yusuf and Osama asked a few minutes ago. The thread scheduling, how the thread scheduling is done depends on the operating system and the thread library. And I'm going to talk it in a few minutes. By the way, we don't call it a race condition, and we will talk about the race conditions later. The term that you use, race conditions, related to multi-process or multi-threads, but the way you used is not correct, and we will talk about it. Okay, I mean, two processes are in competition doesn't mean that they are in a race condition. Not necessarily. Most of the time it happens, but not necessarily. Okay. So, I have three related questions, and I think I cannot hold off those kind of questions. Maybe I should talk about it without talking about. Yeah, okay. So maybe without talking about this, let me try to answer that question, because it keeps coming back and over and over again. So thread implementation, what you are asking me is how the threads are implemented. So basically all of these three questions can be summarized as, does the operating system know about the threads, or it is something to do with only the internals of the processes? There are two types of thread implementations. Okay, in the first implementation, user level threads, all the thread processing is handled within the process. It is handled by the thread library itself. Okay, so there is we have a process table in the kernel. Okay, kernel knows about the processes. Whenever when the time comes to scheduling a new process, it looks at this process table and chooses the appropriate one. Okay, we have a similar thread table in our user space within the process itself. Let's say this process is running 3 threads. Okay, and in the runtime system of the threads, in the thread library, there is a thread table. So all the scheduling is done by the thread library within the process. Operating system doesn't know that there are 3 threads are running inside this process. Operating system doesn't know that there are 4 threads are running within that process. Okay, this is called user level thread implementation. As opposed to this, there is another variation. It is the kernel level thread implementation. In that case, operating system knows that there are processes, multi-processes, and operating system also knows that within each process there are multi-threads, and operating system keeps the thread table. Okay, operating system keeps the thread table. So in order to make a new thread, in this case, in a kernel level implementation of the threads, you need to ask the operating system to make a new thread for you. So thread creation, thread deletion, and scheduling of the threads are handled by the kernel operating system. In this case, to create a new thread, you don't ask the operating system. You make a function call to your library. Make me a new thread. Okay. So obviously there are advantages and disadvantages of both sides, right? So what would be the main advantage of having implemented all these threads in the user space? What would be the main advantage of a user level threads?
Operating system not gonna be too complicated.
Yeah, lighter operating system maybe, yeah, but yeah, okay. What else? But it is not the biggest advantage.
More meaningful thread switches.
What do you mean?
So when the program itself is aware of what kind of threads it is running, it would do
Yeah,
better thread switches.
yeah, you mean that, for example, like this one, like where is that, the web, yeah, okay. If the process knows that this is a special thread, this is important, and these are worker threads, okay.
Yes, exactly.
If one of the threads is dead, I am fine, I have 9 more, okay. But if this one is dead, I am in trouble, right? For when I'm scheduling stuff, this one will be important. So my program knows that scheduling, when it comes to scheduling, this is a special one. Kernel wouldn't know these kind of details, okay? Kernel would not know these kind of details. What else? That's a good point, but that's not the main thing. That's not the main thing actually, okay? So what is the main advantage of implementing? What Yusuf said is okay. What you said is okay, but that's not the main advantage of having the threads in the user space.
Is it managing priority as we want?
Managing the priority, yeah, well, it is related to what Usama said, right? I mean, if you implement the threads in your user space, then everything is in your hand. It is much more flexible. You make your decision yourself, your priorities, your scheduling, and everything. That's right. But that's what you're, so you are saying something slightly similar to what Usama said.
It is
Is
faster
it
because
fast?
it's all user level.
Yeah, who said that? Ebru said that, right? Ebru says that it is faster because everything is implemented in the user space. What did we say about the system calls? System calls are expensive. Why? Because it requires context switch. You need to switch from the user space. You need to switch from the user space to the kernel space. Save lots of data. There is a boundary between the copying of the data from the user to the kernel, and so safety issues and etc. But if you implement everything in the user space, you don't ask, your kernel doesn't know anything about what you are doing, right? So you handle everything in the user space, and it is much faster. It is much faster. What was the idea of using the kernel, the threads instead of the processes? I could have handled everything by writing many processes at the same time using the fork, right? I can do the same thing with the fork, many processes, but I don't like it because each process will be different, and by switching between them is going to take lots of time, context switching. But with the threads, I keep the same address space. So the same idea. Without asking anything to the operating system, I am handling everything in the user space. This is much faster. Okay, it is much faster. Is that clear? This is the main reason why we like user space thread implementations. Other than what the other people said, they said that also it is more flexible. Why? Because in the user space, I can write my own scheduler, right? Thread scheduler. That's very flexible. That's a good idea too. Okay, tell me what is the downside of this one? What is wrong about having your threads implemented in the user space? There is a very one serious problem with it.
More complicated to implement.
No, well, it is not. It is not any more complicated than kernel implementing it. I am just making a library call. That's it. I mean, I am not
Does it
talking.
take
I am not talking about the
user space?
implementation difficulty. I am talking about the efficiency or the usage convenience.
The process.
Does it take more space in the user space?
Well, I am going to use that space anyway if it is in the kernel space. I mean, memory is flexible. I mean, it is either belongs to the operating system kernel or the user. No, it is not.
If the process is blocked, then all threads are going to wait.
Exactly, exactly. Let's say this is our Word application, process Word, Microsoft Word, and this one is taking a backup. This is backup thread, right? T backup. This one says that I am going to write some data to the disk. So this one has to make a system call, right? There is no way that I can take the backup without asking the system to help me, okay? I ask the system to help me write this data to the disk. So the kernel takes the request and kernel says that, okay, I will have to keep you in block state because it's going to take a while to write this data to disk. But these two other threads are actually fine. They say that I can keep formatting my screen or I can get data from the user. Just because one of the threads is blocked, these two others are blocked too. Because the kernel doesn't know that there are other threads within this process. But if I had implemented this thing at the kernel level, okay, kernel knows that one of the threads is blocked and it can schedule another thread from the same process. Okay, and it can immediately switch from one process to another thread, one thread to another thread. Okay, well, switching threads in this configuration is not as fast as this one, but it is still going to be faster than switching between these two processes because address space is going to be the same. It will not be different. Okay, so I hope I answered your questions, those three questions, Yusuf question, Usama's question, and somebody else has asked the question about thread scheduling. So thread scheduling depends. If the kernel knows about your threads, it is scheduled by the kernel. If the kernel doesn't know about your threads, it is scheduled by your library functions and your multi-thread libraries in the user space. Did I answer your questions, guys?
Yes, it was. Thank you.
Okay, good. So let's go back to my original flow. Let's go.
Sir, I wanted to ask one more question about user one.
Okay.
We just said that like when it is blocked, for example, if it wants to write to the disk and if it can't, so the whole process is waiting. It
Yeah.
doesn't switch between threads
Sure, yeah.
in user space.
Yes.
Okay.
It has to be because for the kernel, this process is a single process. It is running a single program. That's it. The kernel doesn't know that there are three threads in it. Kernel is not aware of the parallelism within that process. So kernel thinks that this process needs to access the disk. The disk is not ready yet. It will wait until the data is written there. Okay, so I am going to put you in blocked state until disk is ready. Okay, so it will make you wait for the whole process.
And the common practice is user space, using user space.
I didn't say that.
Right.
I said that it depends on your thread implementation of your operating system. And in fact, I didn't say this yet, but in fact, most modern operating systems, they kind of implement in between, but usually the kernel knows about the threads. But switching between the threads here is expensive. Also making a new thread is expensive. So they implement a hybrid approach and we are going to talk about it.
Can I ask something?
Sure.
Uh, if the condition is like like picture B, threads can still communicate with each other.
Sure,
Because,
yes. They are definitely, these three are definitely sharing the same address space. These four are sharing the same address space. The communication between them is very efficient because they are using the same address space. They are seeing the same global variables, right? These four and these three. So there's no problem, but the switching between the threads is done by the kernel. Also, anything about the thread library, you need to make a system call. That's expensive.
okay, thank you.
Okay, let's go back, and this is the again dispatcher thread and the worker thread. Okay, how can you implement such a system, okay, from the scratch? One thing is use threads. It's very easy. There is a worker thread, there are worker threads, and there is a dispatcher thread, okay, and it works that way. Or sometimes you will say that, okay, I'm going to use a single threaded process, just a single process. There are no multi-threads in it, so no parallelism. That means that there will be only a dispatcher thread. It will take the network request. It will look it up by itself without because I don't have the worker threads anymore. It will look it up from the web page. If it is available, it is going to show it. Otherwise, it's going to load it from the disk, and it will wait for the next connection. So this will be single thread blocking system calls. So that means that while I am waiting for the disk to load new pages, my clients, all of them are going to wait. They are going to wait. So that's not a good solution, actually, the second one. Single thread, no parallelism, blocking system calls. Or again, if I have a special operating system, there are some system calls, okay? You say that I need this data from the disk. And I know that my process is going to be blocked because that data is not available yet. But that operating system says that, okay, instead of I am blocking you, I am going to let you know that that data is not ready. Okay? But I will call you back when the data is ready, but I am going to let you continue. Okay? So this is called a non-blocking system call. You make a system call, operating system either say that, okay, I am done, your data is ready, or it says that your data is not ready, you will not be blocked, but you should know that your data is not ready. I will interrupt you when the data is ready. Okay, again, parallelism, non-blocking system calls with the interrupts. So this is much more complicated to deal with because there might be many requests waiting. Okay, to be satisfied, and it will make your program a lot more complicated because you ask the operating system for many pages to load, and each one is non-blocking system call, and you are waiting for the interrupts for each of them, and you will have to keep all of them in your head, in your memory somewhere. That makes a finite state machine, actually. Okay, so the simplest one, the most convenient one, is the threads or the multiprocess approach. Okay, good. As I said before, previously this was the case before the threads. Each process has a single execution. The idea of thread is this. Okay, this is a resource grouping. Open files, open network connections, memory allocation, and everything. They are all resources. They are grouped together, and there is a single execution. The thread approach says that why shouldn't I think execution as a separate resource? And if I say that instead of a single execution, I have many executions happening at the same time seemingly, and I can call each of them as a thread. That's why they call each thread as a lightweight process. Why is it lightweight? Because it doesn't have to, when you make a new thread, you don't have to create all the stuff that you create for the processes. It is because many things are shared by the threads, such as the address space, which is the most important one. The address space is shared, the open files are shared, network connections are shared, signals, alarms, they are all shared. So many things are shared. That's why they are lightweight. Most importantly, there is no protection between the threads. That makes it very easy to communicate between the threads. Okay, so there is no protection between the threads because we don't want it. We don't want it. We don't want a protection between the threads. I like to use the same address space, and it is impossible actually, because for the protection you need the hardware hub. With the hardware hub, then you need to go to the operating system to switch between threads to threads or create the threads. Yes.
Can I ask a question about the previous slide? Actually, the one before that too. So we said that the third option corresponds to a finite state machine. Does that mean the others do not correspond to a finite state machine?
Well, even if, I mean, of course, you can model everything with a finite state machine, but the finite state machines with these are very, very simple. Okay, each thread has a finite state machine in this case, either busy or not busy. Okay, either doing something or not doing something. And this is, there is only a single thread for this one. There are only states, but with this one, I am handling 5 clients at the same time. Client number 1 is working, client number 2 is not working, client number 3 is working, and each combination, 1-0 combination, okay, when they come together, so it makes 2 to the power n states, and you need to know how to switch from one state to another state, and you need to handle it. Okay, so with this one, let's say I am handling 5 clients at the same time. Okay, now I got an interrupt. Interrupt says that the data is ready. So I need to know which data is ready. When the data is ready, which client has that data, and I need to say that, okay, this is your data, client number something. So I need to keep the track of all that information. That makes it complicated. Okay, let's go on. Classical thread model. There is no protection because we don't need it. We don't want the protection. Okay, the threads, all the threads share the same set of open files. Doesn't matter if it's a user level thread or the kernel level thread. If one thread opens a file, all the other threads is able to access that file. Okay, if one thread gets some memory from the operating system, all the other threads have access to that piece of memory. Okay, so what is specific for each thread? Okay, what is specific for each thread? Okay, that's the idea. For each thread has its own register set. That means that each thread has its own program counter, its registers, its stack. I'm not talking about the stack pointer. I'm talking about the stack. Each thread has its own stack. Remember what I said? Function F1, function F2, and function F3. Each one is considered as a thread. Each one is running separately. Each one can make calls, and each one has its own local variables. So to make calls, function calls, or to keep local variables, each one should have its own stack. And each one should have its own state, either running, blocked, or ready. Okay, like the processes. So these are per thread items, but these are all shared. So address space is shared. Your global variables, open files, child processes, alarm signals, accounting information, all of them are shared between each thread. Okay, good. So when you look at the process table, many things are shared between the threads other than these. Okay, I think this picture is good. So these are the stacks for each thread. Number 1, the stack space for the thread number 1. Thread number 2 stack space, and thread number 3 stack space. You understand? And okay, and these are my globals, and globals are shared. Do you understand why we need the stack space for each thread, right? Because stack is important. Stack is important to keep your local variables. Okay? Stack is important. By the way, maybe this is a very big mistake, sorry. I could say that I have 3 threads and each one is running F1. Each one is running the same function, same worker function. Remember our web server? Each one is running same function, but each one has its own stack, so it is possible. It's like recursion, right? Recursion calls the same function over and over again, but each time when you call the same function, okay, it has its own stack record or its own activation record. Okay, so each one is using a different memory. And when I say I have 3 threads and each one is running function F1, but each one is using a different stack space, that means that they can do whatever they want with their local variables. Their local variables are different, but their global variables are not different. They are the same. They are sharing the global variables. So each function can communicate with each other. Okay? Any questions about this picture?
Can we say these threads are for user mode threads?
You mean these? No, I cannot say that by looking at this picture. I mean, whatever I said here is valid. Whatever I said here is valid for both user level and kernel level threads. For kernel level threads or the user level threads, these are per thread. These are not shared, but these are shared. The idea of threads does not depend on the user level or kernel level threads, okay? That's an implementation detail. I am not talking about the implementation right now. I am talking about the idea of threads.
Can I ask a question?
Sure.
I didn't get where is the threads physically? I mean, we say they have their own stack, but in the processes address space, where are they? I mean, for example, in the heap or?
Thread is an execution, okay? Previously, within a single process, I have this picture only, right? There is an execution. For that execution, I have the stack space and the globals. Now I have three executions, and for each one, there is a stack space, but they share the globals. So wherever I kept my stack, now I am keeping 3 stacks in this process. So the situation is not that different. I mean, where I keep my data is the same, but I have only multiples of them, okay? I have multiple stacks, okay? And I need a way of keeping my register somewhere. Okay, since I have a single CPU, either this one is running or this one is running or this one is running. When this one is running, it is using the CPU's registers, okay? When this one is running, it is using the CPU's registers. So what do I do with the register data of this thread? I keep them in the thread table. If I am using the user level threads, that thread table is in the same process, okay? But if I am using the kernel level threads, kernel keeps that data for me, like the processes. Did I answer your question, Ebru?
Okay.
No, I did not. I mean, what I am saying is that I am not saying anything new. I mean, you keep all the data wherever you were keeping with the processes. Now I keep more copies of the execution. 1, 2, 3 copies. Wherever I kept my stack, I am keeping my stacks in the same place, okay? But I have many versions of the stack. I don't have a single stack anymore. I have more than one stack. And I am using the stack pointer to point to the stack, but since I have only a single stack pointer, I need to, when I switch from thread to thread, I need to keep all that information in a thread table.
Oh, okay.
And this is very similar to switching between two processes, other than the context switching, of course, or the space switching. But again, my CPU can handle only a single thread at the same time.
Where do I keep my thread table?
Well, that's implementation dependent. If you are using the user level threads, your thread table is in your process here. Okay, but if you are using this, your thread table is in the kernel space. So this is your thread table in the user space. This is your thread table in the kernel space. And this one or this one, it is not up to you, it is up to the system. It is your thread library. If your thread library is implemented in the user space, then you have to use this. If your thread library is implemented by the kernel, then your thread table like this. As a user, all you do is make a function call, make me a thread, okay? It is up to the thread library to make that decision. Am I going to make a system call, or am I going to do the thread creation in the user space? So let me show you one example actually. Let me show you one example. POSIX threads. POSIX define the standards for writing a thread-based program. Okay. So these are some of the function calls, pthreads function calls. Okay. So there is a function call to create a thread. There is a function call to terminate a thread. There is a function call for waiting for thread to terminate. And there is a function call that says that I am not going to use the CPU right now. Let some other thread to run. Okay. So this is like a fork. It's not exactly fork, but or the Windows system procedure called make a new process. So creating a thread, terminating a thread, or exiting from a process. This is like wait PID, right? Remember wait PID? When you say wait PID, you wait for your child to terminate, right? And this is for two bookkeeping functions to initialize thread attributes or data needed for creation of the threads. Okay. This one is special for the threads only. We don't have such a function or such a system call for the processes. You say that I am using the CPU, and if I like, I can continue using the CPU. But I am yielding it. I am letting it go. Why? Because I know that there are other threads who wants to use the CPU. So I am yielding the CPU. This is a sign that says that threads are cooperating. Okay? Threads are cooperating. For example, remember our okay, the thread that does the display management. It says that I can continue using the CPU, but for now maybe for a few hundred milliseconds, I can take a break and I can wait until the keyboard thread and this thread does their job, because I cannot make them wait for a longer time. If I do that, interactivity will suffer, or the backing up, taking the backup is going to suffer. So I'm going to yield. Okay? So that's a sign that says threads are cooperating with each other. They are not competing. We don't have any system calls for the processes that say that I am being nice, I am going to give up my CPU. No, you don't say that with the processes. That's not because you are mean. That's because the processes think that they have the CPU for themselves only. Okay? They don't think that there are other processes. You don't write your processes that way. You don't write your C programs that way. Okay? Mohammed, you have a question?
Yes, I have a question. From what I understand, technically you can create infinite number of threads per CPU, technically. But we do not see anyone doing that. Why?
Well, technically you can allocate infinitely large memory spaces, but you don't do that, right? Thread is a resource. Process is a resource.
Okay.
Memory is a resource. So you act responsibly, right?
Okay, now I see.
Technically, you can jump into your car and you step on your gas pedal and you can go as fast as you like technically, but you don't do that because that's very dangerous. I don't understand your question actually. I mean, why threads are different than in terms of creation than creating?
Well, actually, let me put it this way. When we look at
I see storks. Did you see the storks? I see the storks. Leylek gördüm havada. Gördünüz mü? Do you see storks? You don't? Because it is blurred. But I see it. So this is the, just mark your calendars. Storks are back. Okay, so what's your question?
My real question, well, what I was trying to say is when we look at the CPU manufacturers, when there is a two-core CPU, there's number of threads is either 4 or 2, not 5 or not 6. Why?
Oh, you are talking about hardware hub for the threads. So you are talking about something else. We never talked about how the hardware handles this. Okay, so there is, I mean, they don't talk about this anymore, but they changed their terminology. There is hyper threading. You heard about this? Hyper threading?
Yes.
So hyper threading is this. Even if you have this CPU a single core, okay, with the hyper threading, you keep 4 register sets, okay. Each register set 1, register set 2, 3 and 4. Each one has the program counter, program status word and all the registers, okay. So you keep 4 different register set. When you switch from one thread to another thread, all you do is you use this register set or this one or that one. So switching between the threads is very, very fast. Because remember, what is specific for each thread is the register set, right? Also the stacks and etc. But stack doesn't mean stack, just means that stack pointer is pointing to a different place. So with the hyper threading, switching from one thread to another thread is very, very fast because you don't have to save the register information to your thread table, okay, and you don't have to load all the registers from the thread table anymore, as long as you don't have more than 4 threads, okay. So switching between these 4 threads are very fast, so switching time is going to be fast. They cannot do the same idea with the process switching, because switching between the processes means that you need to switch address spaces And switching address space means that backing up megabytes of data sometimes. I don't have that much space in my CPU, but for the threads I have it. Okay, so what you are referring to do is hardware helps to make the threading, multi-threading much faster by giving you these kind of storage spaces in registers. Okay?
Thank you, sir.
Did everybody understand the question and my answer? We never talk about hardware help until Muhammad's question. When Muhammad asked that question, I had to talk about this hyperthreading. Hyperthreading means that your CPU is helping you keep the register information or keep this small amount of information here. This small amount of information can be kept on your CPU. Most cores, they have 4 or 8 way thread space for the registers, okay, and the state. So this is a small amount of information only. So you can keep 8 sets of information like that. So switching from one thread to another thread is just a single clock cycle, or maybe a few clock cycles. Okay. So switching between the processes is much more expensive. Millions of cycles time needed. Okay, but switching from thread to thread is a few clock cycles at most. Okay. Oh, I am out of time, sorry. But you asked many questions there, but that's good, that's good. So, maybe Ebru's question again. Ebru, this is what you are doing. You are just, here is an example. Let me take 5 more minutes of yours, sorry. This is a simple multi-thread program example. Did you start studying your multi-threads in your systems programming course? Are you doing multi-threads?
No, not
Not yet. What are you studying?
Threads are at the very end.
So what are you doing right now? What are you guys studying with the systems programming course?
File I/O.
we are.
Input output.
Yes, file.
Okay, you started from there. Well, you are doing many system related codes and etc. But when the time comes, you are going to write these kind of programs. So there is a function print hello, and I am going to create 10 threads. Each one is going to run this function. So there will be 10 different print hello functions running at the same time. Okay, and this is how you do it. I create an array of pthread structures. I included pthread library. Okay, I create an array of 10 pthread structures, and in a loop from 1 to 0 to 10 printf. Okay, this is the main thread. So there will be total of 11 threads. One of them is this main thread. All 10 of them will be these functions. And I say that create a thread, and thread data structure number I is here. I will not talk about the parameters here, but here is a print hello world. Print hello world is the function pointer here. Print hello world, function pointer, and this is the parameter to pass to that one, that function. So I am creating a thread, and that thread immediately starts running. Okay, when that is 10 of them, when it starts running, it will print a message on the screen with the thread ID, and it will terminate the thread. Okay, if I don't get a nice status back, that means that there was a problem with the thread creation. Okay, that's it. I think I will start looking at this program tomorrow morning. But before coming to class, please type this in and make it run. Try to get answers, and there will be some problems. Sometimes it won't compile, sometimes it doesn't run the way you want. Try to figure out the problems, and we will discuss this program tomorrow. Okay, that's it for today. I will see you tomorrow morning. Your homework number is out. Maybe you have noticed it, maybe you didn't. Okay, you have 15 days. Okay, see you tomorrow morning.
Thank you, sir.
Bye.
Have a nice day.
Have a nice day.
You too.